that's when my life changed. So no big deal. Let me try to get to where I need to go on this computer. We're still working with 2 computers, sometimes 3. Where are we at? Limits at infinity. We started talking about that kind of stuff. And let me give you guys some information on it, right? So this give you guys some definitions. When we talk about limits at infinity, in some ways, here's what they're really looking at. They're looking at the limit as x goes to infinity of a function, okay? Or the limit as x goes to minus infinity of a function. And then hopefully, you know, you have really 3 situations with this, okay? Because you're approaching infinity from what? Well, you can't. You're approaching infinity, or you're approaching what? Minus infinity, not from both sides, but from what? One side. You guys okay with that? So these are limit questions, but they're limit questions that are approaching infinity from exactly what? One side. Okay, because you can't get to infinity from, when I say x goes to infinity, you're really talking about positive values of x. Does that make some sense? Like eventually, to some degree, all these x values are positive. All these x values, as you go to negative infinity, are negative, just so you guys know. All right, you guys okay with that idea? So they're one-sided, so you can only go to a infinity that's really positive infinity for the first one from really, I should say, from the left side, one side. Does that make some sense? And you can only go to negative infinity from really the right side, but it's a one-sided limit is what I want to say. One-sided, not two-sided. And so as a consequence, you might say, well, what does that mean about your answers? Well, let's talk about what that means, okay? That really means this. Your answer is going to be L. I'm going to do it this way. I'll give you a definition, but your answer is either going to be L, and you say, what does that mean for my answer to be what? L. What they mean is your answer is finite. All right, you guys okay with that? So you either have a finite answer, and you say, well, what does that mean? Well, it's like 8, 10, 11, -2, -1/2, 3/4. It's a number. So your answer is either finite, or your answer is going to be what? This or this. And you say, well, what are these other things? Well, that's going to be what? Infinity and minus infinity. These are known as non-finite, okay? They're not finite answers. So those are going to be your 3 answers for every question. It's either finite or infinity or minus infinity, and that's the deal. All right, you guys okay with that one? Let's give you some notation here, though. Sometimes we say this. We say it this way. You know, we can say y goes to L as what? Bless you. X goes to infinity. We say y goes to infinity as what? X goes to infinity. Or y goes to minus infinity as what? X goes to infinity. Or minus infinity, okay? So, I mean, we'll go through some of that notation, but I just want to let you guys know that there's ways to describe our answers, and I'll put the various ways. And even if you go to negative infinity, it's the same idea. It's either going to be finite or what? Or infinity or what? Minus infinity as your answers. Do you guys like the lights on or the lights off? Huh? Off? I have another class, and there's a student in that class who he needs the lights on. Like, I can't see. That's what I said. That's what I said. But I guess he has some vision issues or something. But that's what I said. I said, why don't you move if you have trouble seeing? He said, I can't move. Well, why not? I don't know. I don't know. That's how I see it. That's what I would do. If I couldn't see, what would I do? Move where I could see. Does that make any sense? I don't know. Be good to move. All right, whatever. Okay, let's give you guys some information. Okay. So let's keep our colors. It's either what? Finite or what? Infinite or, negative infinity. Same idea. Those are the options for your answers. That's what you guys are going to see. Now, I'm going to give you the definition that's in your book. And really, here's what they say. Your function f is really defined on that interval from a to infinity. Okay. And that limit, x goes to infinity of the function equals L. And they just mean it's arbitrarily close for sufficient x. This is what the picture is. This is what they mean by convergence, essentially. Okay? So I got to draw my picture. Maybe something like this. Here's that function f. Here's this a value they're going to talk about. But I think the point is, this is that line, y equals L. So the value of the function, in this case, looks like this. This is what they're saying. F goes to L as x gets what? Big. Okay? And what do you guys think this is known as, ladies and gentlemen? You're going to see this is we call this a horizontal asymptote. We're going to give you a definition. Okay? So that's kind of the idea. You're really kind of looking at a horizontal asymptote. That's not how the book defines it, but that's I'll call it that now. You have a horizontal what? Asymptote. And then the other direction, negative infinity. This is how your book would define it. F is really defined on I'll put negative infinity up to a. Those are negative values. And they'll give you a similar situation here, but you're going in the other direction now. Right? You're going to go, for example, something like this. Y equals L here. And I guess we can describe it this way too. We can say f of x goes to now negative infinity, or I'm sorry, f of x goes to L as x goes to negative infinity here. So the focus is really on this left side. They're really talking about, again, a horizontal asymptote. So I want you guys to focus there as you're focusing over here. Okay, so that's kind of the meaning here. You're going to the left forever, and here you're going to the right forever. And if you approach some line L, that's what they mean by convergence. You go to a finite number. So that's the picture, and it's a horizontal what again? Horizontal asymptote. So in pre-calculus, they talked about horizontal asymptotes in graphing. And in calculus, they give you the calculus definition of a horizontal asymptote. So definition of a horizontal asymptote, right? And that is this. That's the line y equals L is called a horizontal asymptote. Okay, if either the limit as x goes to infinity of the function equals L, or the limit x goes to minus infinity of a function equals L. So here's our definition of a horizontal what? Asymptote. It's that line that we just talked about, y is L. I guess we'll keep it blue. Okay, now you might say, and of course this is finite. That's the idea, that this number is finite. That it's a number, that's all. But is either. It's or down here. This is the word or. What's that? Yeah, you see this word or either? I'll share with you the picture. Because if you go in one direction, here's really what's happening. If you go in one direction, like in this picture, if you go to the left forever, what's the story? Your function gets closer to that value L. For large values of x, or I should say, sorry, small values of x, because you're going to the left, that's small, it's a type of small. Your y values are getting close to that L. And you go, what are you talking about? Yeah, they're really talking about all these, in case you guys, right? These are points. There's an x value and a y value. So as x goes to the left, x goes to negative infinity, y is getting close to that number L. And if you say, well, how come that's not on the right? Well, that's not happening on the right side. So the reason they say the or is for that reason. You can go actually in one direction and get close to this value L. It's called a horizontal asymptote, like this picture is showing, because you don't have that right-handed limit getting close to an L. Here, the right hand, not a right-handed limit, going to positive infinity. Here, going to positive infinity, you say, what's the story? You're getting close to that y value being L, not going to negative infinity. Something different's happening there. So this together, these two pictures, if you have either of that happening, you say you have a horizontal what? Asymptote. That's what they're saying. Yes. Never crosses that line, yeah. Because it's a limit. Yes, if it's finite, yes. So we say the line y equals L is a horizontal asymptote. Oh, because y is a horizontal line. Remember in algebra, you describe horizontal lines as y equals a constant. So that's what they're saying here. What's that? No, y equals the finite value L. So this is a horizontal line in beginning algebra, right? Y is L. So what they're saying is if you can show that your function gets close to that number, remember this is approaching. As x goes to minus infinity, that's what we mean by convergent. This is a graphical picture of convergence for limits at infinity. Same thing here. If x gets arbitrarily large and that curve gets close to that L value, you go, what are you talking about again? Well, remember, you got points. This is an x and this is a what? Y value. So as x goes to positive infinity, this is the y value, by the way, for the function. Y gets close to L. You say, how close? Arbitrarily close.
It's more like an approximation, right?
Yeah, you're getting, it's a limit.
Yeah.
You're getting close to that number, arbitrarily close. It's approaching that number because it's a limit. But you call that number L, and the line created by that number, y is L, is known as a what? A horizontal asymptote. You know, this morning I talked about inverse trig functions. And you go, what are you talking about? Yeah, I think I even have it in Desmos here. Let's go back to Desmos. Now, there we go. I was talking about to those trig students, those poor trig students. Because you're talking inverse functions. I have to lecture them like a dad, like I lecture you guys all the time. I lecture the world. Oh, my God. You know, preach. He said, take your trig serious. You're going to see this again in calculus. You know, what you're looking at, we're not going to see this function in calculus 1, but you see this function in calculus 2. And you show that, this is my point to you, that this has actually two horizontal asymptotes. You go, what? There's two? Yes. As x goes to infinity, what does the y values go to? Pi over what? 2. As x goes to minus infinity, what do the y values go to? Negative pi over 2. You see how I have that here? Y equals pi over 2. That's the red line. Y equals minus pi over 2. That's the those are the L values in this picture. And that's for the inverse tangent function. But you say, oh, do I worry about that here, Mr. Judge? I'll say, no, that's next semester. That's calculus 2.
So no inverse function for us right now.
No. But it's in calculus 2. In other words, the thing about calculus 2 is you get to do some of the things you did in calculus 1, but now you do it with other functions like logs and exponentials and inverse trig functions. There's a whole lot of other functions that we can study and apply calculus to. And that's in calculus 2. And, you know, so, but that's coming. But it's kind of interesting because, again, I talked about this morning. And, oh, I didn't know you could do that. But, oh, that's even better, huh? No, did I? No, okay, you can't really do that. Okay. But this is my point. This is the irony, is that's exactly what we're talking about. You can have functions that have actually two horizontal asymptotes, not one. Anyway. So let's give you a very simple calculus 1 question. Is that right? And I'm going to change the color. Oops. Here we go. You see this curve? What's this curve? Y equals 1 over x. You guys okay with that? This is our very first example. I'm going to bring it in here, but we're going to look at that limit here as x goes to infinity of 1 over what? X. That's always your first example. And you might say, I don't know what's happening here, Mr. Judge. Well, there's a couple of ways you can reason here, okay? You see the limit here, x is going to infinity. Is that true? That's the same x. So what we say is y, where is your y value? This is also your y value. Okay? Y goes to what as x gets big? X is getting how? Big. What do I mean by that? Is x 1? No, bigger. Is x 10? No, bigger. Is x 100? No, bigger. Is x 1,000? A million? No, it's bigger. X is going where? To infinity. So what I'm going to do here, I'm going to bring in the picture. Just to start, and notability, add to existing note. Okay. All right. There we go. Here we go. You say, what's happening? Okay, let's get out some details. Remember what I said? This is an x coordinate. This is a y coordinate on the curve. You guys okay with that? That's the point xy. What's happening as this x value goes to infinity? X is getting bigger, bigger, and bigger, and bigger forever. What's going on with the corresponding y coordinate values?
Approaching 0.
They're approaching what? Y goes to what? 0. So this is the graphical approach. These are all my y values over here. Maybe I'll use purple or blue. Y is getting, well, I can't even draw an arrow, but sorry, the arrow won't even go through. So the y values are, these are the corresponding y values, right? They're getting closer and closer and closer to what? To 0. Now, do they ever equal 0? No. But they get close to what?
0.
These are all the corresponding y coordinate values. Okay, so this is a graphical approach. So what you're seeing here now is exactly what I'm saying, that the y coordinates, which are also known as what? This is y, which is 1 over x, goes to 0. We can say that equals what? 0. Is that finite? Yeah, it's a number. So the line y equals 0 is a horizontal what? Asymptote. That's really what they're asking for. It's limit at infinity. The graph is really what's happening. So that's kind of an important idea. Now, I want you guys to also note, you say, what do we have to note? We're going to note also that the limit x goes to minus infinity of 1 over x is also 0. And you might say, why? Well, where are you going to now? You're going to minus infinity. Minus infinity is a type of small. Why do I say it's a type of small? Because the further to the left you go, the smaller the number. And now, here, this is what they're saying here. If I can ever get the right tools. This is where x is. Corresponding y coordinate now. These are x and y coordinate values. What's going on with all those x values? You're going to the left forever with those x values. You say, what does that mean? I'm going to the left. Well, you're getting not bigger, but what? Smaller. Those values of x. What's going on with the corresponding y values? They're approaching what? See all those points? They're approaching what now? 0 as well. So this is the graphical approach to the question. And sometimes we say y goes to 0 as what? X goes to minus infinity. Or they put 1 over x goes to 0 as x goes to what? Minus infinity. Okay? Now, just to kind of throw this out there for you guys, maybe I'll give you with the book a fact from the book now, or how about if I just go to Desmos here? There's nothing special about 1 over x. You can have y is 1 divided by x to the second power. Okay? So graphically speaking, what do you guys notice about this? As x gets big, y goes to 0. Is that right graphically? As x gets small, negative infinity, y goes to 0. In fact, you could do that all day long with what? Y equals 1 divided by x to the what? Third power. Don't you have horizontal asymptotes again at what? Y is 0? Okay, you can see that graphically. So your book is going to say to you this question. The book is going to give you this now. It's going to give you this fact. And this is the fact that we're going to use for this section. This is like the main fact. It's a main theorem. They call it theorem. If R is positive and is a rational, right, fraction, then the limit as x goes to infinity of 1 over x to the r equals what? 0. That's essentially what I was saying to you guys. And then, if r is positive and is what? Rational. And they'll say, such that x to the r is defined for all x. We're going to see what they mean by that. See if you guys can see what the difference is. Then the limit x goes to minus infinity, 1 over x to the r equals what? 0. Do you guys know why they have to say that? Because what's the difference between the first and the second statements? Do you guys know the first and the second statements? Here, x goes to infinity. Here, x goes where? So in other words, up here, this is going to go back to what I mentioned. Your values of x are what? Positive, and over here, your values of x are what? This is why they say this portion has to be what? Defined for all x. Can't be imaginary. It has to be real. That's all. Like if I said to you, can you take the square root of a negative? No, that's what I mean, because r is a fraction, like r is 1/2. So, I mean, if you said, I want to see what you mean by this statement. Right? I want you guys to look at the note here. The limit as x goes to infinity of 1 over the square root of x, what do you guys know? This is like saying 1 over x to the what? 1/2. This is what they mean by being rational, a fraction. It's infinity. Okay, we're going to know that this equals what? What do we know about going to infinity here? Your values of x are what? These x values are positive. You're getting bigger, bigger, and bigger. In fact, that function is defined for what? The domain of that function has to be x greater than 0, by the way, right? X can't be 0. That's the domain of the function. So that limit makes sense. You say, why does that limit make sense? Because the values of x, if you're going to infinity, you're thinking, okay, x is 1, 10, 100, 1,000, x is big, or positive numbers. But what doesn't make sense is if they said, okay, what about this limit? That doesn't make sense. Why does this not make sense? Your x values are negative. Your domain is a set of all real numbers that x is positive. So this is what they mean by this number 2. If r is rational and positive, such that x to the r is defined for all values of x, then you can say the limit is what? 0. So you can't really apply this at all because it's not defined for negative values. So in other words, nobody can ask you that question. They throw it out. It doesn't make sense. You can't see what happens to x as it goes to negative infinity if it's not defined for negative values. That's just the idea. That's the idea behind that. So I know it looks like a detail that people look at that and go, what are they talking about? Why do they have to give me that information? Well, because people will think, well, what about, people can answer this limit question, but they can't answer the other one. Okay, people say, okay, I can take the limit as x goes to infinity, but why can't I do it for minus infinity? Well, because it's not defined. And if I even looked in Desmos, right, having dinner, here's the function. Graphically, don't you have a horizontal asymptote at 0? Because as x gets big, y coordinates get closer and closer to what? 0. Easy peasy lemon squeezy. It's not too bad. I don't know about you guys. You did do this in pre-calculus, by the way. You might say, no, I didn't. Yes, you did. But they didn't. They gave you an algorithm. They gave you something different, right? Do you guys remember what I'm talking about? Did you guys even take pre-calculus? Maybe not. No? It's like some of my poor students from another class. It's horrible. Okay. Oops. Let's do it nicer. You have me thinking about something. What to say about this? Do you guys know what's happening with this limit question? If they give you that one, how do you think we think about this one here, right? What do you think? Well, I would think of it this way. It's still going to be 0. You're right. I'm going to say x, factor out the x, and you got x squared minus 1. Okay, let me just go with that for you guys. This first x, because you guys know this limit here is getting what? X is getting big, right? That's the same x. That's the same x. So how I think about it is the first x is getting big. Maybe we should put some notes. But what does that mean about x squared? X squared is also getting what? Big. Does that make sense? If x is getting big, x is 1 billion. Square it, it's even bigger. Is that right? If it's 1 million, square it, isn't that even bigger? Now, what would you say? Where is x squared minus 1 going to? Just so you guys know. It's still big. Is that true? Yeah. Because even if you subtract 1, it's still going to be big. X is getting big. It's getting big. So here's my point to you. If you take this x squared minus 1, this is also getting what? Big. The point is your denominator is getting what? Big. Is that true? So if you said, what's 1 over, what's that ratio now? 1 over something that's getting what? Big, and bigger goes to what? Good, goes to 0.
It will be like 0.0000.
1 over point, 1 over like $1 quadrillion or whatever, if that's even a word. That decimal is close to 0 is what we're saying. So I'm going through the thought process behind deducing that this limit is what? 0. Now let's see if you're really awake. Let's note. How do you think you would handle the thought process if you said, if x is going to minus infinity, 1 over x squared minus 1. Now the limit is going where? To negative infinity. Where should that be? Where should this equal still? It should be 0 still. You say why? Well, the values certainly are negative. Is that right?
Yeah.
So what I would say is, well, this means if x is going to minus infinity, my x squared is going to what? Isn't that positive infinity if you square it? If you say I'm taking negative a billion, you square it, it's going to now be positive and very big. So if I subtract 1 from it, it's still really big. Is that right? But x squared minus 1 is going to what? Isn't that negative infinity? Why would that be negative infinity? This is going to minus infinity. This is going to plus infinity, right? That's a product there. Okay. Now, what about 1 over all that? X squared minus 1. That's going to go to what? Still 0. Why? Why does that still go to 0? 1 over a small number? Is that true? Is that 0? Okay. Let's see. Desmos? 1 divided by x squared minus 1. Oop, that's 2. You guys remember these nice curves from pre-calculus? Do you ever have to graph these in pre-calculus? You go, I have a horizontal asymptote and a vertical asymptote. Where's the horizontal asymptote? Y equals, I'm going to use this one here. I screwed up. So there's an undo. See that y equals 0? So it doesn't matter if you go to the right or you go to the left, it's still going to be what? 0. Okay, now let's go to a pre-calculus question. You say, what do you mean by pre-calculus? You guys want to get used to this here. You're going to see this kind of a lot, right? They say, what's the limit? X goes to infinity. 2x squared plus x over 3x squared minus 4. This is a prototype question in Calculus 1. Okay, this is kind of like a standard question in Calc 1. Oh my God, and it was even in a pre-calculus. Because they give you that in pre-calculus. You say, what do you mean? They ask you, can you give me the horizontal asymptote? You go, yeah, I know what it is. Y is 2/3. You guys remember that algorithm? That's your horizontal asymptote. Korea calculus. You guys remember that? You have to go through graphing polynomials and rational functions. Pre-calculus. Okay. But what's the calculus approach? Here's the calculus approach. You want to go to the denominator. Go to the variable with the highest power in the denominator, okay? Right here, it's x squared. That's the key. I think I'm going to put that in red. Okay, here's the statement. Use the variable. How about if I say this? Divide every term with the variable with the highest power in the denominator. That is your calculus 1 key. That's the key. A lot of your questions, you're going to do this. This is like the essence of the whole section. Say that's the heart of the section. So you first identified the variable with the highest power. It's x squared. You guys okay with that? And then the logic behind it is actually very simple. The algebra makes sense. You say, why does the algebra make sense? Well, I'm going to do this. Here's the algebra. Okay? Is this true, by the way? What do I mean by that? Isn't those two terms on the right divided by each other equal to 1? Isn't 1 times any fraction itself? This is the logic behind it. This is why you do what you do. You might say that's a kind of a random statement. No, it isn't. It works out algebraically. So what I'm saying here is by the algebra, you're essentially doing what they're telling you to do. Limit x goes to infinity, 2x squared over that x squared minus x over x squared divided by what? 3x squared over x squared minus 4 over x squared. That is exactly what they said to do in the first place. You're dividing every term with a variable with the highest power in the denominator. That x squared, you're using this always, always, always. But there's the algebra, by the way. So now you might say, what happens with this algebra? Gone, gone. You guys okay with that? So you're going to look at the limit now, x goes to infinity, 2 minus 1 over x divided by 3 minus 4 over what? Is it okay, plus. Good, we'll keep it plus. Okay, you guys okay with that? That's really what you're seeing. Now you might say, well, what comes next? What comes next is you use properties of what? Properties of limits. Let me show you every detail. What do they mean by properties of limits? They mean this. Limit of a quotient is what? Quotient of limits. Okay, you guys okay with that? Limit of a sum of limits. Limit of a constant times a function. You get to pull out the what? Constant. You guys okay with that? You pull out that constant. So you have the limit of 2. Well, let me do this. I can do that in an iPad, and this kind of, I can pull out the constant. Okay, you guys okay with that? So let me say this. You guys know where this limit goes to. Where does that limit go to? Say 0. Where does this limit go to? Say 0, even though you have that constant. You guys okay with that? Where do limits of a constant go to? The constant, yes. So algebraically speaking, or with arithmetic, 2 plus 0 over 3 minus 4 times 0 is what you're seeing. I'm showing you every detail. Okay, so that's really what's going on with this question. So now you get, what's this limit equal to? 2/3. That's finite. So, ladies and gentlemen, we showed that this limit is really what? 2/3.
Professor?
Yeah.
So during a test or like homework, do we have to write out the proof?
Have to write out what?
The proof, like this.
I mean, you have to show some work,
Yeah, true. You can't just like, yeah.
you know, but you don't have to do all the details I did. I do it so that people can see the logic, so you guys can believe me. And you go, okay, I'm going to do that. You know, divide every variable with a what? Highest power in the denominator. And this is, again, this is a Calculus 1 question. You get to see this again in Calculus 2, sort of, but they expand on it. And I'll remind people in Calculus 2, hey, remember what you did in Calculus 1? You know, that's what you do. So this is a very standard Calculus 1 kind of question. So that just means you have a horizontal asymptote where? Yeah, this is how you formally answer that horizontal asymptote. You say y equals what? 2/3. You know, that's the formal answer for a horizontal asymptote. And if you graph it, you'll see that. You know, if you graph it in decimals, I won't do that, but standard question. And similarly, they say, okay, what's the limit now? X goes to minus infinity, x squared plus 3x over 5 minus x. Okay, you might say, okay, this is another rational. So when you have that rational, you're going to have to divide every term by what? The variable with the highest power in the denominator. What is that? X. You guys okay with that one? So the limit as x goes to minus infinity, x squared over x, 3x over x over 5 over x minus x over x. So this gives you x plus 3 over what? 5 over x minus 1. All right, this is going to be interesting, ladies and gentlemen. Interesting. Now, I can show you guys another way to look at this here, right? Can I say, can I separate this idea into a numerator and a denominator? Okay. Where does your numerator go to? Let's write down the logic. X is going to minus infinity. Where do you think x plus 3 goes to then, the numerator? Maybe x is negative a billion. What's negative a billion plus 3?
Still negative.
Okay, that's negative a trillion. Negative a trillion plus 3. It's still going to negative what? So I can think of my numerator going to negative infinity. You okay with that? What's the denominator going to? You say, what does 5 over x go to?
0.
Good. And then 5 over x minus 1 is going to what? Isn't that negative 1? So what I'm saying is this will go to 0, and that leaves you just with what? Negative 1. You okay with that? So my numerator is going to negative infinity. The denominator is going to negative 1. Ladies and gentlemen, what do you think that means? Sort of. It means this goes to what? Infinity? Because you have that negative over a negative.
Yeah, positive.
See what I'm saying? You're going over, you're saying, what's that negative over a negative? It's going to be positive. So if I go to decimals on this one, right? Remember, this is the original question. The limit's going to negative infinity here. So x squared plus 3, 5 minus x, 5 minus x. I think I have to do it this way. Okay, what do you guys notice about that curve? See all the points? And I guess I can't touch, yeah. See these points? X is going to negative infinity. Where's the y value going to? Where's the y going to? It's going up forever. Is that right? Isn't that going up forever? You know what that means? Y goes to positive infinity. So we can say it this way. Yeah. We can say it this way. As x gets big, where does y go to? Infinity. The y coordinates are getting big. And that's what Desmos is saying here. Even if I scroll and I take points on that curve, x going negative infinity, y is getting big forever. That's again what I started to describe to you guys yesterday. Remember this, end behavior in college algebra and pre-calculus. You guys remember that? This is end behavior. So if you studied pre-calculus, this was a type of end behavior. You're going, this is the y value going up forever. If you guys remember that. So you had different kind of ways y's can go. Y can go up forever. As you go to the left, it could go down forever. As you go to the right, it could go up forever. It could go what? Down forever. That's those end behavior pictures. And that's kind of what you're studying when you say limits at infinity. We're studying end behavior. You know.
The end behavior from the numerator and denominator though? Because we got
With-
negative infinity, negative 1.
With the logic we just went through here. X is going to negative infinity. What that means is, even if I add 3, and x is going to negative infinity forever, that still means what? That term's going to negative infinity. That's my numerator. The denominator, the first term, is going to 0. So that first term, which goes to 0 minus 1, is going to go to that negative 1. So this is why we put negative 1 here, negative infinity on top, and we say negative over negative is a positive. Infinity divided by 1 is still going to be what? Infinity. So you're going through this situation. I think, I'm trying to remember from pre-calculus if they had that. I think they did. But I have to remember the pre-calculus. What happens when the numerator is larger, the power in the numerator is larger than the power in the denominator. Yeah. Say that again. This was a different question. Did we do it? Oh, sorry. Yes. Did we do it here? Yeah. Okay. Okay. If you're, yes. So this is as x goes to what? Negative infinity. Y goes to positive infinity. This is really the calculus. This is still calculus notation, but you'll see it more in detail. Calculus 2, I guess, but that's how they deduce. This is how you deduce these answers. If you did all those details that way, if you said, I want to do it this way, okay. And you can. You said, I think I would rather say the limit of x plus the limit of 3. You guys okay with that? Using properties, that would be 5 times the limit of 1 over x minus the limit of what? 1. And again, you got to see where this is going, negative infinity. Now you might say, okay, which do you want to handle? We'll handle each one separately, okay? How about this? If x goes to negative infinity, where does x go to? Negative infinity. Isn't that the question? That's the same x, ladies and gentlemen. So that goes to what? Okay. Where do constants go? Stays the same. Good. All right, where does this go to? 1 over x. Does that go to 0? Where do constants go to? Stays the same. Is that true? Let's write down what we have. Negative infinity plus 3 over 5 times 0 minus what? 1. Is that true? So I want you guys to now think of the logic here, okay? We got to be careful with what we're working with. We do got to be careful. There are some things that have to be. If you owe $1 billion and you paid off, you gave $3 to your debt. I hate to say this to you. You might as well think of this as what? Owing $1 billion still. Okay, you don't like $1 billion? If you owe $1 trillion and you paid $3 to it, the owing, it's negative. You still kind of owe $1 trillion. Does that make sense? We got to be careful with our arithmetic. Yeah.
So at what point does the number, let's say there was a number other than 3, at what point does it become significant enough like not to just cancel it?
Never.
Unless it's another infinity?
Never. Because limits are what? They're not finite numbers. So you might say, okay, when is that big enough to pay off the debt? You never. Because x is going to negative infinity. It's going to an idea. It's not even a number. So what I'm saying is if you add 3 to that, it's still going to negative infinity. Because that, remember, it's changing, right? It's going to the left forever. But it's an okay way to think of if you say, okay, I owe that money because it's negative. Now, the denominator is a finite value, so that's why you say that's negative 1. Because 5 times 0 is 0, 0 minus 1, that's negative 1. And then you can use the logic still of negative over a negative, which would be what? Positive. Now, there's limits to this logic. You go, okay, what are the limits to the logic? Well, this is part of the course that we're studying. This is really part of calculus. this is not 0. This is not 1. I don't even like to use the word limits because now you go, well, what's a limit with limits? There's problems. In other words, this is called indeterminate forms. These are the two indeterminate forms that we'll see in calculus what? 1 and calculus 2. You see it in calculus 1, sort of, but you'll see it in more detail in calculus what? 2. Now, you might say, what if I see it now? Like, they might give you a limit question with a polynomial, and they will. Go, Mr. Judge, they just gave me the limit of x squared minus x. Just to give you guys an example of what I'm talking about. This is an indeterminate form. This is a big no-no. You're going to say, is that infinity minus infinity, and that equals 0? And I'll say, no, that's an indeterminate what? Form. What do you think indeterminate means? Can't determine. That's all it means. It means you can't deduce this. And you might say, why? You just got through telling me, you know, that x, if you use properties, right? I'm saying, I like the properties. I just want to blindly follow those things. And x goes to infinity. You go, I like that. Okay. Isn't that infinity minus infinity? I went through the properties. And I go, yeah, but this is not finite arithmetic. You say, why? Well, what's going on is x is approaching infinity. X squared goes to infinity much faster. So what's happening, what's under the hood here, this is going faster than the other. This is faster. This is what? Slower. Because every time you score a number, doesn't it get big? So the problem is you don't know where that difference will be. Will it be finite? Will it be infinite? You don't really know because x is approaching getting bigger, bigger, and bigger, a large place, sort of, an idea. So then you say, okay, Mr. Judge, what do you do then if it's indeterminate? Well, you fix this. How do you fix this? You guys know how you fix it? The fix is to use what? Algebra. So you're going to hear me say that over and over again. What's the fix? Use what? Algebra. You say, what's the only algebra you can do here? Factor. It's the only algebra. So that question becomes limit as x times x minus 1 when you what? Factor. Okay? Now, here's the logic again. Here's what you say. X is getting big. Is that true? So, okay, we know as x gets big, x is getting big. I got to find the right tool. You see this x right here? That's the same x. So x is getting big. Where's x minus 1 going to then?
Still big.
It's still big. How do you know?
Just minus 1.
Well, let's say you have Oprah money. $1 trillion. And guess what? She lost 1. She still has some what? Big money. You guys know what I mean? So I can take that I could do a little bit of this thought process. And then now you say, what's x times x minus 1 then? That's still infinity. So ladies and gentlemen, this is what? This is infinity. You say, really? Yeah, this here is not 0. It's what? Infinity. And that should make some sense because why? X squared grows much faster than x. And so we write this as x gets big, y gets what? Big. That's end behavior. That's the horn going up in pre-calculus. If you guys remember polynomials and those horns. And behavior. So if you don't believe me, you go to Desmos. Everybody believes Desmos. So you say y equals x squared minus x. There's the end behavior. Sorry, it's a polynomial. You know, we can fix this, I guess. You know. So this is what we're saying. As x gets big, every point on that curve for the y coordinate gets what? It's getting bigger forever. So we call it end behavior. As x gets arbitrarily large, where does your y coordinate value go? That also gets arbitrarily large. That's what this is. But there is two indeterminate forms you got to watch out for. Infinity minus infinity and infinity over infinity. And then the fix is to use some what? Algebra. And the algebra used is different depending on the situation. And it's not as hard as you think because there's only so much algebra you can use. Like here, the only algebra you can use is to what? Factor. So welcome to what? Limits at infinity. I hope you guys learned something. And, you know, we'll see some more examples tomorrow. If you guys want to see more examples, where do you find them? Oh, my gosh. Good for you. You might for lunch. You say, I'm going to have a, what are you guys having for lunch? Sandwich, soup. You might look over, because we'll see more tomorrow, examples tomorrow. We got over some of the basics today. You know, you might even look at limits at infinity. Go, boy, we got some more examples for tomorrow. You guys okay with that? All right. See you guys later. Have a great day. Take care and stay safe. Okay. But the dean actually thought it was a bot. I said, I don't think so. I think I seen her. I seen the bot. Maybe. Could it have been a bot? They show up in person, the bots? Because I know they apply for financial aid and they take the financial aid money. So could finally somebody just, could it be actually a person assigned? I don't know. It's weird. He says, no, it sounds like it's a bot to me. Okay, well then, if I call the police on the bot, will it matter? Weird. Okay, we got a like. Thank you. That must be Shannon. She might be home. All right, let's do some limits at infinity. You guys ready? Because we might see this on our test. You go, oh, Mr. Judge, is this a what? Why did I put that x cubed in purple? Divide it's the variable with the highest degree in the denominator, okay? So, ladies and gentlemen, let's try this out, okay? Yeah, maybe I'll share with you guys. I'll show you. Prove it. School might get mad. Don't be doing that. So fix the bot problem, please. Okay, going to divide by everything by the what? Variable with the highest power in the denominator. And ladies and gentlemen, here we go. Limit x goes to infinity. Is that 1 over x? Is that minus 4 over what? X cubed over 1 plus 1 over x squared minus 1 over x cubed. You're the twin. I don't know, Shannon. I don't know. How do you prove a student's not a bot? I don't know. All right. What do you guys do with this one? I don't know. I mean, I know this. If you wanted, you might use, like we did yesterday, maybe for some people, they like that we did every gory detail with properties of limits, okay? And I'll do that for you guys here. Remember, I do have videos online if you want to see extra examples. Okay, so have you guys do that. Okay, you guys good with that? Now, sometimes they do this notation that way because they don't want to write x goes to infinity for every one of these, you know. So I just want to let you guys know if you see that in a solution somewhere, that's what they mean. But what's the first limit? Do you guys know what this is? Yep. Pretty simple, is that right? And then what's this limit? Yep. And what's this? Okay, and what's this? Good, and what's this? Look at that, ladies and gentlemen. Not too bad. So say, is that 0 over, remember, this is 4 times 0, by the way. And that's going to give the whole thing to be 0. 1 plus 0 minus 0. And I think you get 0 over 1. Be careful. What is 0 over 1? 0. So, ladies and gentlemen, this limit equals 0. And it means you have a horizontal what? Asymptote on that line 0. I won't go to Desmos and show that to you guys. All right, you guys okay? Easy peasy lemon squeezy? Yeah, I kind of like that one. You know, let's go over a little bit of details. This isn't that bad, but there are some that are kind of a little tricky, I would say. But we'll get there. All right, number 2. Okay. So you might say, hey, what's the limit here now of x goes to negative infinity? And sine. Now, I don't see if I remember, but I want you guys to know, first of all, that on the right side, you guys know what you're looking at here? Let's go over the details. This here is a what? Composition of what? Of functions. That's a function in a function. So you can think of that back in the day. I might have showed that to you, f of g of x. Do you guys know what I'm saying? How do you guys start that? You start that by what? Working with the inside function, g. The inside function is g. The outside function is what? Is sine. That's f. Okay, so that's a composition of functions. Now, x goes to negative infinity. You guys okay with that? So you say as x goes to negative infinity, what do you have to do? You work with the what? The inside function. You work your way inside out. So x is going to negative infinity, and you have to find where pi, which is a constant, it's not a variable, over x squared goes to. So that will be pi over x squared. Where does that go? Do you guys know where that goes? What do you guys know what's going? This is the same x, by the way. So what do you think is going on with that x? It's being squared. Yeah, so a constant over a very big number. You say, how do I know that's very big? Like if you put x being negative a billion, square that, it's now positive, I don't know what that is. So you have a big number on the bottom and a constant in the numerator. That means it goes to what? Okay, you guys okay with that? So down here, this is super big and positive. Does that make some sense? Okay, now, this is kind of nice because what do you guys know about sine? Sine's a real nice continuous function. So really, how you go about this now is to say, hey, where does sine of that number go to? Okay? Well, this portion here, the middle portion goes where? This is going to 0. So this means this is sine of what? 0. This is something you do with continuous functions. And these functions will be, and I guess this is the orange part now, but I want you guys to see that detail because that's something that, you know, that happens especially a lot in Calculus 2. And they toss in some of these questions in Calculus 1, and sine of 0. Do you guys know what sine of 0 is? What's this? What's sine of 0? Do you guys know? That's 0. So, ladies and gentlemen, this limit equals what? What do you think? That limit equals 0.
Did we just get one answer?
Yeah, you don't have. It's only going to be one answer. It's either going to be a finite number. 0 is finite, so it's fine, or it's going to be positive infinity or negative infinity. And then the book did something here that I'm going to talk about right now. You know, what did the book do? You know. But before I do that, let me give you guys another variation here, okay? Note, they can ask us the same kind of question, but I'm going to change it. This is in the same family in my mind. What if they just do what if they just do this? Okay, they might say, what about 3 over, this was x squared? I don't know, 3 over x. How's that? This is in the same family. So in other words, you got the inside function and you have the what? Outside function. So you say this is as x gets what? Big. 3 over x goes to what? 0. So you're going to have to do the what first? Inside function. Okay. And so you're going to now work with the outside function, which is cosine, because it's compositions again. And say cosine of what? Cosine 3 over x goes to cosine really of now what? 0, because that function for cosine is nice and what? Continuous. What's cosine of 0 though? This equals 1, doesn't it? Isn't cosine of 0 1? Oops, I got my colors wrong. So just to kind of compare and contrast, this limit equals 1. Where is it here? So there's your answer. Okay, you guys see that there? Cosine of 3 over x as x goes to infinity, that's end behavior is 1. I might even look at this in Desmos because I kind of like that. You know, you go, this is the curve, ladies and gentlemen, by the way. But that's the curve. Look at the curve around 0. It's not this question isn't around 0. The question is where? At infinity, is that right? It has a horizontal asymptote where? At 1, by the way. If I can. Yeah, this is where 1 would be. So, you know, these are some interesting curves.
Professor, I have a
Yep.
question.
Yep.
For the sine one, can we also, do we have to write out like pi and 2 pi, stuff like that?
Pi and 2 pi, what do you mean?
I mean, you can get like several answers.
No, you can't. This is only one answer. This is sine of pi over x squared as x goes to negative infinity. So you say y equals sine now of pi divided by, what was it, x to the what? Is it third power? Second power? Okay. Okay. So here's my point to you. This is the curve, but you're going to negative infinity. There's only one answer. You're getting closer and closer and closer to what? the x-axis, and that x-axis is the line y equals 0.
So we can only get one also.
There's only one answer here.
Professor,
Yeah.
can we do it like in, we can't do it like how we did it in the first question?
Well, this is the first question, by the way. Why is sine of what do you mean? The first example we did? Mm-mm. No, because you know why? You have a good question. Let's make this clear. The question is, can I do it like what I just did here? The answer is no, because you don't have what's called a rational function. This approach applies only for rational functions, where r of x is p of x over what? Q of x, where p and q are polynomials. So, you got a nice polynomial, a rational function here. These are now trig functions. In fact, question 3 is a monkey wrench question. Okay, now here's a monkey wrench question. This is now the book, the author of this book, I think he gives us on the homework. And this is similar to, might be why some people are saying there's two answers, right? Because what happens here now, this is not a rational function. This is a what? Trig function. Here says as x goes to infinity, okay, your sine curve goes where? This is why some people made the remark, it goes to two values, right? And I got through saying, no, it can only be one. Well, this is a very special case. It kind of goes beyond the course, but the author did ask this. And you might say, what's going on here is x goes to infinity, because this is end behavior, remember? What happens for values of x going to infinity? This oscillates. So here's the answer they'll say. Sine oscillates where? Between plus and minus 1. So, because sine oscillates between plus or minus 1, sharing that with you in Desmos even, you go, what's going on as x goes to infinity? Well, they're saying it oscillates between plus or minus 1. Remember the definitions of horizontal asymptotes. That is not like this picture, does it? Even though it's a sine curve, it is not like this picture. It is not like this picture going in the other direction. Can't remember which one it was, but it doesn't matter. The point I'm making is these two examples do not what? Oscillate, do they? In the way that what? Sine does. So you might say, oh my God, what does that even mean? Is it going to two values? I would say this. It oscillates between what? Plus or minus 1. And then you said to me, Mr. Judge, what does that even mean? Well, this is what it means here. That this limit, and this goes, again, beyond the scope of the course, this is a flavor of does not exist. There's flavors of does not exist. So your book might even say that in back of the book. I don't even remember what the book says, but it might say, hey, limit does not exist because it oscillates between plus or minus 1. And you go, is that the same kind of flavor of does not exist that we seen earlier? And the answer is no. It goes now to a more deeper does not exist. And there is a deeper does not exist. This is where it is. So they do, the book does toss that. This author does. But this is not a two-sided limit. It's a one-sided limit. So don't confuse that. You say, where's the other side? There's only one side. Yes? Yeah. The same will go, and that's what I was going to do as a note. You might say, and it doesn't even matter. You can go to positive infinity or even negative infinity. It won't matter. It's the same conclusion. It's that flavor of what does not exist. And that's in your text. But other calculus books may not even give these questions, in a calculus 1 setting. They might save it for a more advanced calculus kind of setting. I don't know. I haven't made it yet.
I mean, this is like beyond the,
No, it's if it's in your book and your homework, there it is.
okay.
Huh? Yes, it is. It's very simpler. I would say these are the things I write in my notes in red. That's why I put it in red for you guys. Because this is kind of how when I used to take notes, I would do that. You know, so it doesn't even matter if it's positive infinity or even negative infinity. And you're right, these questions in some ways are easier.
Is it gonna be different for tangent, because the graph is different?
It's actually the same for tangent because of the fact that tangent is a periodic function, you know, but they're not going to ever ask that. But I've never seen that even in an advanced calculus course.
So also now the secant and stuff like that?
That wasn't her question. So remember, what is limits at infinity and minus infinity? Do you guys remember? This is about end behavior. End behavior, meaning what's going on at the ends, not in the middle or anywhere. It's at the ends. So number 4, all of these questions are end behavior questions. They go back to the pre-calculus days, college algebra really as well. And they're asking, you know, you guys might have had some variations of end behavior. Gosh, what happened? But that, you know, but that's even these days what's going on. What happened to this iPad? I'm going to restart this, okay? Never happened. This stuff has never happened in my life. Come on. So we'll be back. It's coming back. And it might even be. Oh, there we go. Okay. All right. So, number 4. This is a very good question here. Okay, so this question here is kind of like what we talked about yesterday. You want to really be aware that this is the limit of x minus the limit of what? Square root of x, okay? It is a limit of a difference, right? So if x gets big, what's the story? X gets big minus even the square root of x, that's also going to be what? Big. Because x is, this is getting big as an idea. It's not a finite number. Now, once you see this, what do you guys know? This is a what? It's indeterminate. Indeterminate means you cannot determine. That's what indeterminate means. All right? So, can't determine. So, again, you use what here? Yep. Now, this might be new because in the calculus course, you do learn some new algebra. You say, what do you mean? This goes back to that worksheet I did for you guys. X minus, this is x to the first, minus x to the 1/2. Do you guys look at that worksheet, by the way, I hope? Factor out the greatest common factor. What's the greatest common factor? X to the smallest power. X to the small, this is the GCF, times that quotient. You say, what's the quotient? Well, go back and divide. It'll be x to the 1/2 minus 1 now. That's the quotient. So I did that for you guys because, again, historically, students have needed to see that. So this is now going to be determinant, meaning you got the limit of a what? Product now. Limit of product is product of limits. Limit. X goes to infinity. Square root of x times limit. X goes to infinity. This is square root of x minus 1. So x is getting big in both of these cases, right? So it doesn't matter. That's the same x. What does this give you? Infinity times what? Infinity. So this actually is determinant, by the way. Meaning this goes to what? Infinity. It's kind of like thinking you got Oprah money times Bill Gates money. Do you guys know what I mean? Oprah money times Bill Gates money, that's just a whole lot of what? Money. So this limit equals infinity. And that's the end behavior here. And remember, if x is going to infinity, x is positive. So we're good with the square root. And in Desmos, y equals x minus square root of x. This is what they're saying, the end behavior. The y coordinate is increasing without bound, just like x is. So as you go into the right forever, that's the end behavior. And I remember in those pre-calculus courses, the picture of end behavior here, you know, this is kind of how you write it with calculus, and this is the notation. And they write that little picture like going up like a parabola. And that's what that all means. That you're going up like a parabola forever. Those of you guys that remember those courses, you know, they do that. It's the end behavior. That's what you're studying is end behavior that was in a pre-calculus course. So that's 4. 5 is the same way.
Professor, I have a question.
Yeah.
For number 4 that you just did, can we use conjugate? So
I wouldn't. But I don't know. I haven't tried using the conjugate for that at all.
I tried and I got the same answer.
Okay. Yeah. Well, that's kind of the remark I made. They won't do that. You say, why won't they give you that question with going to negative infinity? You know why? Square root of x. Right here, it won't be defined. So they won't give a negative infinity in that question. Even if you look at the Desmos curve, you can see it's not even defined for negative values of x, right? So it doesn't, they won't give you that. That question defaults to x is 0, goes to 0 in all honesty, and that will be 0. But, you know, they won't, they should not give that to you. No, you can't, because x could never be negative. But, you know, we don't have to make it kind of that complicated, but they won't give that because it has to be, that's kind of the statement I gave yesterday, if you guys remember that statement. But here, this is interesting. Right? The devil's in the details. You say, okay, x to the 4th plus that limit, what? X squared. Why is this one interesting? Do you guys know? What's going on with x now here? You're going to negative infinity. That's x. So what do you think's happening here with this? This is going to be what? Good, infinity. Plus what? Yes. So then that will be also what? Positive infinity. So what's infinity plus infinity? What's Bill Gates money plus Oprah money? Same thing, a whole lot of money. So the end behavior is similar here. Remember the picture, just want to kind of give you some notation, right? They'll say as x goes to negative infinity, y goes to positive infinity. And I remember the book looking like this, doing the end behavior that way. Because you're going to the left forever, right? X goes to negative infinity. That's going to the left forever. Y is going up. And x to the fourth plus x squared, you can even see that in Desmos, right? Y equals x to the what? Fourth plus x squared. So you're going up, that's like a parabola. It looks like you're going up forever to the, as x goes to negative infinity. Y is going up forever too. So I just want to say this is not an indeterminate form. This is a what? Determinate form. It's determinate.
What if it was x to the fourth power divided by x? Can you divide infinity by infinity?
No. No. But be careful because x to the fourth divided by x will be x cubed. But if you say, so you got to be careful. But yeah, there is no, there's two indeterminate forms you're going to be concerned with. That's infinity over infinity. Okay? And you might say, no, what are the two indeterminate forms? Infinity minus infinity, but it's also the same as negative infinity plus infinity, by the way. Infinity over infinity, and it's even plus or minus, by the way. So these are all indeterminate. The others are determinate. So let's go back. And you actually, indeterminate, you study this in a lot. Well, there's a way to do these kind of questions that you study again in Calculus 2. At least some of these questions, because these are not the only indeterminate forms that exist. There's others. But in Calculus 1, they only show you a couple of them. And that goes back to, you say, well, what do you mean a couple of them? That goes back to your rational function questions. Like if you said, what's this limit? A very simple question. Right? You go, oh my God, what's that limit? Infinity over infinity. That's indeterminate. Oh no, you can't what? Find that limit. Okay, what do you do in every indeterminate form? You use what? Algebra. But the algebra you can use depends on what you have. Again, the standard tool for a rational function always is to do what? Divide every term by the variable with the highest power in your what? Denominator. And that means it's just what? X. That is the algebra that you use here. So, ladies and gentlemen, you get what? One plus 3 over x over 2 minus 1 over x. Limit. X goes to infinity. That's really the question. So this is the algebra that you use with the indeterminate form of infinity over infinity when you have a rational function. And you might say, I know what this limit's going to end up being. What's this limit going to be? It's 1/2. Is that right? So you might say, I've seen enough of these kind of questions. I know this limit's 1/2. So that infinity over infinity is not true. It's an indeterminate form, meaning we cannot determine, but now you got 1/2. Okay, you guys see my point with that? So I just want to let you guys know, yeah, the indeterminate doesn't matter if the signs are positive and negative in either cases. You can have positive infinity over negative infinity. It's still indeterminate, or vice versa. That's what they mean. Because a lot of times they just think it's only infinity over infinity, and it isn't. You do the same rational function approach with the algebra here. And that leads me to a very, just remember, this is a question in a textbook, I believe, right? Anybody know? It might be. It's from my memory. Okay, this is kind of a textbook question. So, all right. So you say, what do I do with this textbook question? All right. Well, we just got through saying, what's the numerator go to? Infinity. What's the denominator go to? Infinity. Is that true? It's indeterminate. And so now you go, oh, I got to use some what again here? Algebra here. Yeah, that's a 9. 9x squared? Yep. So you might say, what's the variable? He said, Mr. Judge, I have to divide what? Every term by the variable with the highest power in the denominator. What do you think that's going to be? I'm going to say this to you guys here. Let's focus on this algebra idea. You got x plus 2 divided by square root of 9 x squared plus 1. I'm gonna do that variable with the highest power in the denominator again here. Okay, but it's gonna be every term, but I'm gonna start by doing that square root of x. Or I'm sorry, just x. And you might say, why am I dividing by x? Does anybody know why? You got the square root of, I know it's the square root of 9x squared, right? It's the square root of 9x squared, but what is the square root of x squared, by the way? So if I change my color here, do you guys know the square root of x squared is what? What is this? It's the absolute value of x, isn't it? Which equals what? Do you guys know what I'm saying? Isn't that the pre-calculus definition? The square root of x from pre-calculus is the absolute value of x. And what does that even mean? That is x when x is greater than or equal to 0. It is minus x when x is what? Do you guys remember that? But you might say, well, which one do I use here? This is the definition of a piecewise function. The square root of x squared is x, but that's only if x is what? Greater than or equal to 0. It is x. Why can I say in this case it is x?
It's positive infinity.
right here. X is going to what? X is going to positive infinity. So you might say, are you cheating the square root of that 9x squared, right? Well, think of it as the square root of x, because that's, again, in a sense, the variable with the highest power in the denominator. So this is why you're looking back at the book, and they have this x plus 2, which is x over x plus 2 over x. We just have to understand what's going on right here with a 9x squared plus 1 over x. Okay, we have to understand that algebra. One plus 2 over x divided by the square root of 9x squared plus 1 over x. And then you say, I don't even know what to use here, Mr. Judge. How in the world do I do any more of that algebra? Right? Over here, my focus over here is an issue. Would you guys agree with that? Because you have the square root function. You go, well, how do I handle this with the square root? What do we do with that square root? Well, what we do with that square root is you go back over here. X is square root of x squared. Is that right? Isn't it true that your x is the square root of x squared? Because that's what this means here and here. X is positive. So replace this with what? The square root of x squared. So in your denominator now, you say, oh, isn't that 9x squared plus 1 over x squared, which is the square root of what? 9x squared over x squared plus 1 over x squared, which would be what? 9 plus 1 over x squared. And that's in your denominator. So some of these things, I just have to say, it goes back to, really definitions. Okay, so can you guys find the limit now as x goes to infinity? The answer is what? The answer is yes. So if you wanted to use properties of limits again, okay, you can say, is that the limit of 1 plus 2 times the limit of 1 over x divided by square root of what? The limit of 9 plus the limit of 1 over x squared. This is all by properties of our limits here. This is properties of limits. What happens now with all these questions? What's this limit? 1, what's this limit? 0, what's this limit? 9, it's still under the radical though, and this limit is what? 0, so you get 1 plus 2 times 0 over square root of 9 plus 0. And that will be 1 over the square root of 9. That's 1 over 3. So this is how you handle that particular question. That's 1 over 3.
Professor, I have a question.
Mm-hmm.
Can we just split the square root?
What do you...
Square root of 9x squared plus square root of 1?
No, it's a good question. This is something you guys want to know here. Here's a fact. This is the recommendation here. The square root of a plus b is very much not the square root of a plus b. That was the suggestion in the denominator. And it's not a valid statement. Right? The square root of a sum is not sum of square roots. The square root of a product is product of square roots. The square root of a quotient is quotient of square roots. But the square root of sum is not the square root of the sum of square roots. Yep, that's a good question, but it's unfortunate that we can't do that. I think, though, the next question about this particular question, just so you guys know, really, because I have that in my notes here to remind students, it might even be in your book, and I don't remember, but what happens if they change this now to going to negative infinity? Now my x values are what? Negative. And it's the same process. You're going to end up getting in the numerator negative infinity over what? Positive infinity. This is still an indeterminate form. You got to use algebra still. This is why I'm saying that. And the algebra is still going to be the same. Let me do it like we started here. X plus 2 over what? X divided by the square root of 9 plus what? 9x squared plus 1. Over what? Is it x? So we're going to have to go back and remember a detail we have way over here. Where was it? Yeah, over here. Focus on this. You see this square root of x squared? What is the square root of x squared going to be now? So that square root of x squared is going to be what? Negative x. So instead of saying here, which means x is minus what? Square root of x squared. So down here, you're going to replace this with now what? Negative x squared. Or negative square root of what? X squared. And so really, at the end of the day, that negative sign will give you the following. You get 1 plus 2 over x divided by minus square root of what? That 9x squared plus 1 over what? X squared. So that negative sign, to emphasize, comes out. So that have that negative sign there, 1 plus 2 over x over square root of 9 plus 1 over x squared. You're going to get a negative what? 1/3 as a answer for that limit question. Okay? So that negative sign comes out. Now, if you look at Desmos, you go, in Desmos, what does that look like for us? Well, y equals parentheses, I guess. x plus 2 divided by square root of 9x squared plus 1, I think. 9x squared plus 1. And you can't, well, let's do y equals 1/3. Y equals negative 1/3. So you might say, well, what are you doing? Well, x goes to positive infinity. That y is 1/3 is a horizontal asymptote. Guess what? This function has 2, because as you go to negative infinity, y goes to negative 1/3 is the other what? Horizontal asymptote. So this has 2 horizontal asymptotes. And that's what I wanted to share with you guys here in this picture. Really, the 2 horizontal asymptotes. That's the function. So that's a question, I think, in your book. And I mean, I might even just put that in what? Let's enter this thing in. Just to complete with these. Never know when these videos will go public. You never know if Elon Musk is going to buy these things. What do you guys think? I hope. It's kind of funny. I met some people out in Silicon Valley, and they say, we have a proposal for you one day, Daniel. Those are the horizontal asymptotes, and that's the algebra that we use for it. So, ladies and gentlemen, we're out of time. And again, if you wanted to see additional examples, go to my website. This is kind of where the Silicon Valley people came in and said, we want to talk to you one day. Woo! Maybe Elon Musk might be. Contact me. Here's limits at infinity. Oh, look at that. Does that look familiar? Number 6 is similar. If you guys want to see number 10, there's a video. That's the conjugate. Number 10 is an indeterminate difference, or sum, but it's really called an indeterminate difference. So the video is right over here if you guys want to see that. And this is from your homework, so I'll see you guys when? Monday. Stick by the Canvas announcement. I put that optional stuff for you guys in writing. And take care, stay safe, have a wonderful weekend.